Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my pleasure to welcome Hoare Strickman from Technion. He's been working on a lot of things, including decision procedures and translation validation. And he's going to talk about his most recent interest on regression verification, which is pretty interesting. So, Hoare.
Yeah, thank you. So I hope this works now. Okay, so this is a replay of my talk at Callees. I think Shuvendu is the only one here who was actually there, so I'm not going to feel sorry for the rest of you. It's a joint work with my student, Benny Godlin. I started the talk, I mean, in retrospect, maybe I would build it a little bit different for this crowd, but at Callees, I started by talking about the fact that in some sense, functional verification has always been like the holy grail of the verification community. And it's also like the main pillar of the grand challenge that Tony Hoare declared several years ago. And obviously this problem is undecidable, but what I want to claim is that suppose that we even ignore the question of completeness, suppose we even look at cases that we can actually prove, there are still two major hurdles. One of them is that functional verification requires functional specification, which is normally quite hard to write for real programs. And of course, the other problem is complexity. And this reminds of a known quote by George Polaya, who said that for every problem that you cannot solve, there is an easier problem that you cannot solve. And what it tells us basically is that don't jump too far. Try to solve the easiest problems from those problems that you cannot solve. And what is this problem that I'm referring to is regression verification. So this is what we're trying to kind of push and I'll try to convince you that this is a worthy problem to work on. And it has these two properties. It's easier than functional verification, but not just that it is still useful. I will even claim that it's actually even more useful than functional verification in some sense. Okay, so what we're going to talk about is like we want to develop a method for proving the equivalence of programs, but not any programs. We're talking about similar programs. It's a practical problem. I've given this version of the program and the consequent version of the program. It has one clear advantage, one less clear advantage, but it's still a big advantage. The clear advantage is, of course, that you don't need to write specification. Right? The former version of the program is your specification. And it is also computationally easier, and this is what I'm going to try to convince you in this talk. Why is it computationally easier? Okay, and I will give you a hint, and the reason is that once the two programs are mostly similar, or most say 90% of the code hasn't changed, there are various ways in which you can abstract your program and decompose your programs to the granularity of functions that makes the verification challenge much easier from the computational point of view. These are the pros. Okay, before I'll talk about the cons. And specifically, we can say that what we want is ideally is that the complexity of the problem is not going to be proportional or exponentially related to the size of the programs that we're trying to verify. Instead, it will be somehow only exponential in the gap between the two programs, whereas it will be, for example, linear in the size of the actual program. So, for example, if I'm giving it the same code exactly, it's going to be linear time to decide that it's the same program. And this thing was a major design consideration in the design of our system, how to make it only depend on the difference. The disadvantage of this approach is, of course, it defines a different notion, a weaker notion of correctness, because I'm not doing this against a specification. I'm doing this only against a previous version of the same program. And yeah.
So if I just, without that slide maybe, what I would have guessed things are just the other way around. If I think of programs from the weakest precondition perspective, then the program is a predicate transformer, that is a function from predicates to predicates. If I have to compare two such things, I compare two predicate transformers, whereas if I have one program and a specification, if the specification is given as a pre and post condition, I have two predicates, and it seems easier to compare two predicates with a predicate transformer than it is to compare two predicate transformers.
Okay, so the reason I'm saying it might be easier is under the assumption that most of the code hasn't changed. Okay, so other than that, it's people have worked on program equivalence as a special case of functional verification for many, many years. Okay, and there it wasn't easier because they never exploited the fact that the functional structure is similar or whatever, all of these things. Okay, we have two prominent examples. One of them is regression testing and in hardware verification equivalence checking, showing that this concept of proving things with respect to a previous version of the same program is a very, very strong idea. It's a very successful method. Okay, regression testing is definitely by far like the most used testing methodology, and equivalence checking in hardware is much more, it's used much more than model checking, for example, which you can say is the equivalent of functional verification. And this is much more successful than model checking exactly because of the two reasons that I mentioned before. First of all, you don't need specification, and second of all, it's easier computationally. Okay? So we have a very good analog.
So,
yes?
So my understanding of regression testing is that you write some functional property that you expect to hold across different versions.
Regression testing, at least in one of the versions of regression testing, you can say that for the same inputs, the two versions of the program return the same values, or prints the same file, like writes to the same file, or have the same screen as output, or whatever. So this is what I mean by regression testing. That's like the most basic regression testing you have.
So
yes.
Hardware equivalence checking, you mean that you say it's easier than like property checking?
Yes.
It's because that they share. The two versions of the design may share major.
Yeah. So in hardware, when you're doing equivalence checking in hardware, you usually assume some cut points in your hardware description, saying that it has to be equivalent from these 2 points to these 2 points. So you definitely use the fact that it's very similar structure, and your transformations are only like because of layout and all sorts of things like that. That the general structure is maintained. Okay.
So are you also talking about sequential equivalence checking or combination?
No, I was talking about combinational actually.
So is sequential also equally successful, or is it?
I actually don't know what's the status of
current
tools of current sequential equivalence checking in the industry. I think it's not very successful as far as I know, but I don't really know. Just to show you that this is a very, very old problem, what I'm talking about. The problem of proving equivalence, not the problem of regression verification. So this is Hoare's original paper from 1969. An axiomatic basis for computer programming. And I found like in the last lines of his paper, so this is the original paper, like in the end, he says the following. So many axiomatic treatments of computer programming tackle the problem of proving the equivalence rather than the correctness of algorithms. And these are references to papers from the 1950s talking about program equivalence. So this is just to show you that this question was considered a very long time ago. I was never able to actually track down these papers. But again, this is just taking the problem of algorithm equivalence, of program equivalence, without ever using the fact that most of the code is the same. So we're actually tackling an easier problem. I will mention a little bit previous work. It's definitely not exhaustive. In the theorem-proving world, there has been, mainly in the ACL2 community, there has been a lot of work on program equivalence. But again, first of all, it was not an industrial programming language, and we were doing it for C programs. And the second thing is, as far as we know, nobody there, again, took this assumption that most of the code is the same, and therefore there was no use of this property. They never used the fact that the two programs are very similar. There has been some work in the last few years about proving equivalence of industrial programs. But all of these made very strong assumptions. All of them worked on loop-free and recursion-free programs, and they always assume that there's no dynamic memory allocation and so forth. So under these assumptions, this problem becomes very easy. So like Intel, for example, published like in 2005 it is, For example, how do they prove equivalence of microcode, which is a very serious problem that they have. They use it all the time. So basically, they just assume there are no loops, or they only consider this for programs that there are no loops, and then they just take every 2 pairs of paths in the program and send it to a theorem prover to prove that these are equivalent. So you can do many things once you don't have loops in recursion. So what we want to do, we want to develop, this is the structure of this talk is going to be, first of all, I'm going to talk about some notions of equivalence. What do we mean when we say the 2 programs are equivalent? I'm going to show some proof rules, like Hoare-style proof rules, that we're going to use in order to establish correctness according to these notions of equivalence. And then I'm going to talk about a prototype that we built for verifying the equivalence of C programs based on these rules. And this prototype, first of all, it incorporates these proof rules. But as I said before, it's important to emphasize that it is sensitive to the magnitude of the change rather than the magnitude of the programs, which is something that I said before. OK, so let's talk about notions of equivalence. The first notion of equivalence that I'm going to talk about is partial equivalence. What does that mean, that 2 programs are partially equivalent? We say that they're partially equivalent if every 2 executions of P1 and P2 starting with the same inputs and these computations terminate, then they terminate with the equal outputs. Okay, so this is partial equivalence. It's not hard to see that establishing partial equivalence is undecidable. Here is another notion of equivalence. It's called mutual termination. Given equal inputs, P1 terminates if and only if P2 terminates. This is, of course, undecidable. Here's a third notion of equivalence, reactive equivalence. This says that if we have P1 and P2, 2 programs that do not terminate by definition, but if these 2, if we're looking at 2 executions which consume the same input sequence, then they also emit the same output sequence. And then this is, of course, undecidable as well. We can talk about K-equivalence. What does it mean, K-equivalence? It means basically that, without even reading what it says, just think about the fact that you unroll all loops K times and all recursion, you limit it to the depth of K, and you expect every 2 executions of P1 and P2 with the same inputs to result in the same outputs. This is the only notion of equivalence that is decidable in this set of definitions. You can talk about full equivalence, which means that P1 and P2 are both partially equivalent and they mutually terminate. And this is, again, undecidable. And you can talk about total equivalence, which means that P1 and P2 are partially equivalent and both of them terminate. I will have a slide soon summarizing all these notions. Okay, so you might see the resemblance in the terms, like this corresponds to total correctness of Hoare, saying that you prove something that it's correct but also terminates and so forth. This is, of course, undecidable. So these are the 6 notions of equivalence. The last 2, we saw some references to that used very similar definitions from 30 years ago in some cases. We saw these notions of equivalence used in the context of testing. Like these references are actually on papers on testing. K-equivalence was actually used without using this name by the paper that I didn't mention, but it was written on one of the slides that Ellen Hu did. So basically, that's what they also did. They just like unroll the loops several times, and then they try to prove equivalence. So K-equivalence was also used before. Yes.
So in program, you say input and output of programs, right? Mm-hmm. So in programs that have state, is output a projection of the state on a bunch of variables, or is it the entire state?
No, it's a projection on the variables that. So as we discussed before, so what we're going to define as outputs is the return value of the function and all the global variables that are being written to by this function. This is basically the outputs of a function.
When you say K-equivalence,
yes.
do you restrict yourself to computations that naturally end after k, recursion to depth k, and loops are unfolded k times, or do you do something?
No, okay, so I will redefine it. So it says that there is no path, there's no pair of paths starting from the same inputs, and uses each of the loops not more than 6 times, or any recursion not more than 6 times, that results in different outputs. Okay? Okay, so, sorry, so I'm going to, so most of the talk is actually going to focus on the partial equivalence. If we'll have time, I can also speak a little bit about mutual termination. Reactive equivalence is much more complicated. I'm not going to talk about this in this talk. K-equivalence from the theoretical point of view is quite straightforward, and these two are just combination of the others. So I'm going to focus mainly on 1 and a little bit on 2. So we want to prove partial equivalence. So let's start with a very simple example. So suppose that we have just a function here and function there that they call themselves. They don't call any other function, and they don't have loops. Okay? How do we prove the equivalence of such functions? These functions have the same prototype. I'm mapping them to one another, and so forth. So how do we want to prove the equivalence of A and B, and the question is, how are we going to prove this? Remember that this is undecidable. So what I'm going to do is, before I'll show you the proof rule that we're going to use, I'm going to remind you of a proof rule which is 38 years old. This is Hoare's rule for recursive procedures. Before I'll explain it, let me just read the quote from Hoare's paper from 1971. He says that the solution to the problem of proving a property over a recursive function is simple and dramatic. To permit the use of the desired conclusion as a hypothesis in the proof of the body itself. Okay, and let me show you what this means. So there's no pointer here, right? Okay, whatever, it doesn't matter. Okay, so as you can see, oh, actually I can use the mouse. I guess, is this? No, that's not, okay. Oh, I have a cursor, or I don't?
You could just point to the...
Yeah, just it's higher than me. Okay, well, as you can see, look at the consequence. The consequence says that if P holds before the program, then Q holds after the program. But you can see that exactly the same thing, we're taking this as a premise. And you can think about this as a proof by induction. What you do is that you assume, oh, that's a laser pointer, thanks. Okay. Yeah, okay. So what we do, we assume the PQ relation on the inductive call. The same way as in induction, we assume something on the previous version of the statement. And if making this assumption allows us to prove the PQ relation over A, but where in A we erase the recursive call. I'm going to demonstrate this in the next slide. Then this establishes the PQ relation. Okay, it's just a proof by induction. I'm going to, and indeed, by the way, proving the soundness of this rule is also based by induction, where the base case of the induction corresponds to the base case of the recursion. Something of that sort. You can think about this way. It's a very intricate rule, and there are several PhDs that were written only on this rule, including Ed Clark's PhD, by the way. And so I will demonstrate this. So suppose that you have a function A, you want to prove the PQ relation, and you have a recursive call to A. So what you do the following. It's like you erase the recursive call. You assume this, you take as a premise this PQ relation. And if using this premise you can prove that the PQ relation holds, then this proves the PQ relation. Okay, this is what it means. So basically what you need to do in a deductive proof, you need to prove that if P holds here, then P holds there. And you need to prove that if Q holds here, then Q holds there. And then using the premise that if P holds here, then Q holds there, you establish the PQ relation. This is how a deductive proof of using this rule works. Okay? Now, what I'm going to show you is that I'm going to use a very similar principle for proving the equivalence of recursive functions. Okay? So this is how the rule looks like. Again, what we want to prove is the partial equivalence between A and B I'm going to use this as a premise when proving the partial equivalence of the bodies of these two functions. Okay? Really exactly the same idea. So how does it look like if I demonstrate it here? So again, what I'm going to do is I'm going to erase the recursive calls, and I'm going to assume that they are partially equivalent, A and B. What does that mean? It means that if the inputs are equal, then the outputs are equal. Remember, this is what it means to be partially equivalent. And if making this assumption allows me to prove that whenever they start with the same inputs, then they result in the same outputs, then I proved partial equivalence of the two programs. Okay?
So inputs and outputs here would be the calling context of the function.
Think about this as an isolated pair of functions. Then the inputs would be the arguments here and every global variable that you read along the function, for example. And the outputs is, as I said before, the return value and the global variables to which you write. Okay?
So it's an assumption on scalar programs here, or
the assumption what?
on scalar programs, or this could
On
be
scaled programs?
programs with only scalar variables, or they could have maps as well, heap in other words.
Doesn't seem like it would matter.
Doesn't matter.
It doesn't matter. So what I will show you later on, that we prove the soundness of this rule for some language, some restricted language. And as far as we know, except one case that we still suspect, it is also sound for C. There's some problem we might have with the stack that we are not even sure if it breaks the soundness or not, but I will talk about this a little bit later on. Okay, so how can we use this rule? So as I told you, in Hoare's rule, we were using, it was built in the context, it was used in the context of a deductive proof. And we're not doing a deductive proof here. We're trying to do some model-based proof. So we can basically do what the rule says, which is just like erase the recursive calls and add some kind of a premise or something like this. But the most convenient way that we found to use this rule is to do the following. We just replace the recursive calls with a pair of functions that have two properties. On the one hand, they over-approximate A and B, so we are not going to lose soundness. And by construction, they're partially equivalent. Okay, so this thing that when we're putting two functions that are partially equivalent by construction, this is where we use the premise. Okay, and I think that anybody who is a little bit familiar with these things knows that the most natural way to achieve these two goals is to use uninterpreted functions, because uninterpreted functions obviously over-approximate the functions, and by definition they are congruent, which congruent means that they are partially equivalent, basically. Okay? So after we replace the recursive calls with uninterpreted functions, we can reformulate the rule that I showed you before. So the way it's going to work is the following. I'm denoting by A superscript UF and B UF, AB, after I replaced the recursive call with a call to the same uninterpreted function. So this is what we called isolation. We isolate the function from its callees. Okay? So far I'm talking in the context of a single function calling itself. Remember, I will later generalize this. Okay? So now we can rewrite the rule as follows. We can just say that if we prove the partial equivalence on the isolated versions of these functions, this proves the partial equivalence of A and B. And the good news about this is that this is a decidable problem, even for like C programs. Okay? Okay, so I'll show you an example. So suppose you have these two recursive functions. You don't have to understand them, just these two functions basically compute the greatest common divisor. These are two recursive functions, so GCD1 calls itself here, GCD2 calls itself here. We ask whether they are partially equivalent. So remember, what is the first thing we need to do? We need to isolate these functions, which means that we have to replace the recursive calls with the same uninterpreted function. So that's what we're going to do. We're going to replace it with U. So now it's not the original program, so I added this UF as a superscript. And now it's a flat function, right? There's no loops, no recursive call, no nothing. So we can compute the transition function of these two functions. We can compute the inputs, it's just a and b, and x and y in this case. And we can know what the outputs are, g and z. And with this information, we can go on to prove the premise of this rule. In this case, that if the inputs are equal, that is, a is equal to x and b is equal to y, and I'm performing these transitions, then the outputs are the same. Okay? And this is obviously decidable. Okay? So this is the example. This is the first example. So now, so before I generalize this, any questions until now? Or, yeah.
So let's say the two functions differ by additional parameter that the user introduced. How would this rule look like in that case? So let's say that
like in addition to, you mean A, B, so you're going to be...
C also in
yes.
the parameter list.
In both sides or on one side?
On one side.
Okay, so that's, yeah, so that's a problem. So we assume in the beginning that we have some kind of mapping between the functions. And practically, we only map functions that have the same prototype. Okay? What you can say is that it's like you can make a different definition of equivalence when they don't have the same inputs. Okay, then you can say, okay, so assuming that they have the same values of inputs for which this input is defined in both programs, or something like that. But this is a different definition of equivalence. Okay?
Can you touch the idea of transition function?
Yeah. So once you don't have loops or function calls, you can just compute basically an expression that tells you what are the legitimate computations that are going on in here. Okay, so this is what I meant. So this is what you put into the. So you can just compute. So these are the transitions that I'm referring to here. Okay. Yes.
You said your words were that it's obviously decidable. Suppose that one multiplies by 2 and the other one shifts. Then you need definitions of all operators in the language to some extent. So
it's all decidable. This is the type of stuff that CBMC does. Just think about this as. I mean, do you know how CBMC works? Or so it basically breaks everything into a propositional formula.
And it does so by restricting the bit length of.
Yeah, it assumes it's 32 bits or something,
okay, yeah,
or 64 bits or whatever. Yes.
Yeah.
Okay, so now let's generalize this. So far we looked at just a pair of functions that are calling themselves. Let's generalize this. What I'm going to generalize it to is I'm going to generalize this to strongly connected components in the call graphs. So we might have mutual recursion, for example. Okay? So we will assume for now, first of all, no loops. Why no loops? Because we can always turn loops into recursive calls. And we will assume a one-to-one map between the recursive functions of both sides. Later on, we will relax this restriction, but for now, let's assume this restriction. And we will assume that mapped functions have the same prototype. And we're going to use the following notation for a function f. uf of f represents the uninterpreted function by which we replace f, such that f and uf of f, they have the same prototype. And if two functions are mapped, then they have the same uninterpreted function. Okay? And then with these things, with this notation, we can have the following rule. So first of all, I used this notation before. The idea is that a superscript uf is a, where I replace each function that is called in a with its uninterpreted function. Okay, f is replaced by uf of f, if f is called in a. And with this notation, the new form of the rule is this thing, is if I prove for every pair, every mapped pair, the partial equivalence of the isolated versions of the program, then I can conclude that for each pair, they are partially equivalent. Okay, so in the next slide, I'm going to show you how we use this rule for the case of mutual recursion. Okay, so how does it look like? So suppose that, for example, we have on one side we have this mutual recursion between G and F. On the other side we have G prime and F prime, and they are mapped. That is, G is mapped to G prime and F is mapped to F prime, and we want to prove the partial equivalence of G prime to G and of F prime to F. So the rule in the previous slide, what it told us is basically the following, that we need to prove separately these two things. We need to prove that F prime is partially equivalent to F while replacing the G functions with uninterpreted functions, and the other way around. Prove the partial equivalence of G and G prime when replacing F and F prime with an uninterpreted function. So if we prove both of these things, we can conclude that these functions are partially equivalent pairwise. Okay, is that clear? Okay. I will show you a small improvement, but it's important in practice. In practice, what we might have in our call graphs, we might have strongly connected components that are not exactly, they don't have exactly the same topology. Only some of the functions are expected to be equivalent. Okay, so the rule so far did not know what to do with this, but what I'm going to show you now, that it's actually sufficient to find a mapping between these strongly connected components that just break all cycles. Okay, so if we had here 4 of them here and 2 of them here, if I could break all cycles in this strongly connected component of 4 by mapping some of them to some of them here, this would be sufficient. So in this case, for example, suppose that I only want to here, choosing G and G prime, for example, is sufficient to break all cycles. So I will only prove equivalence of G and G prime. Okay, remember that in the previous slide we needed everything to prove the equivalence of all pairs. So the idea is that only when calling functions in this map, we replace them with an uninterpreted function. So let's see this illustrated. So we're going to replace the call to G and G prime with a call to an uninterpreted function. And now we're going to prove the partial equivalence of G and G prime. Now this will establish the partial equivalence of G and G prime without establishing the equivalence of F and F prime. And this sometimes is the only thing that we need, because imagine, for example, that G is what is being called from somewhere from the root. So we don't really care, maybe we don't really care about the partial equivalence of F and F prime. The only thing we need is the partial equivalence of G and G prime. Okay? Okay, let's go to the next case. The next case is that we have one strongly connected component calling another strongly connected component. So what we do in general, we compute the DAG of the strongly connected components. And we just go bottom up. So assume, for example, that we prove the equivalence of H and H prime. Then we can just abstract them again with an uninterpreted function, which is non-recursive. And then after we abstracted this with an uninterpreted function, you can think about this just as inlining. You can just inline this up. Okay? So I show you the various strategies that we can apply in different types of call graphs. I will show you this now, how the general algorithm works. That it's like a decomposition algorithm. So what you see here is 2 call graphs of 2 programs. They're a little bit different. For example, F2 is calling F7, which doesn't exist here, for example. Some of them are syntactically equivalent. The green ones are syntactically equivalent. We have one recursion in this case. So what our algorithm does, it just goes bottom up. So these functions are clearly partially equivalent because they're syntactically equivalent and they don't call anything else. So we just replace them with an uninterpreted function. These two, the same thing. Now we go up. So now we want to prove the equivalent of F2 and F2 prime. So we check the equivalence of F2 to F2 prime, where this one, you can think about this as being inlined. It's not really inlined, but I will speak about this later. You can think about this right now as being inlined. whereas these two calls are being replaced with a call to with the respective uninterpreted functions. So it might work, for example, if some of the code here moved to here, right? It will still work. It will still be able to prove the equivalence of this to this if we took some code and moved it to another function. So suppose that we failed. We could not prove the equivalence. Then we go on. We try to prove these two. Suppose that we failed. Now we try to prove these two. Remember, now it means that I'm replacing the recursive call with a recall to an uninterpreted function. Suppose it was successful. I replace it with an uninterpreted function. Now I can eliminate this, and I go up. Now I'm trying to prove these two against these three, while replacing the others with an uninterpreted function. Okay? So this is how the algorithm goes bottom up. Let's take another example. This time I have a strongly connected component, which is, of course, not non-singular. So I'm going to go quickly over this. The only thing I want to show you is that now when we try to prove the equivalence of F2 and F2 prime, look what we're doing. We will assume that these two are uninterpreted, although we did not prove that they're partially equivalent yet. We'll just assume that these are uninterpreted and try to prove the equivalence of F2 and F2 prime. If yes, we're going to have a special status, a special color, which is called equivalent if MSEC, never mind the name. But the idea is that it's not equivalent yet. We first have to do it on the other side as well. Okay? And then we're going to continue. We're going to try to prove these two. Suppose we failed. And now we're going to try to prove the equivalence of F5 prime and F5 while assuming that these two are uninterpreted. And if we were able to prove this, then now all the elements of the strongly connected components passed the test. And only now, remember the inference rule, only now we can conclude that these two are partially equivalent pairwise. Okay? And then we go up. Okay. Questions about the decomposition? Yes?
Can you go back one slide, please?
Yes.
So in this case, when you're checking F5 and F5 prime,
Yes.
to inline F6 inside F5?
Yes. Okay. Okay, let's talk a little bit about soundness and completeness. So we proved the soundness of this rule, of the rule that I showed you before for a simple language, restricted language. As far as the restrictions are not very important, but the important thing is as far as we know, it is also correct for C. There was some. I showed it once to Malay Ganai, and he raised the question of what happens if you manipulate the stack backwards. That is, in the Callee, you go backwards on the stack and manipulate the caller. These are the type of crazy things you can do in C. And I think that he's right that this might actually hurt soundness. I'm not entirely sure. I still have to think about this. But even if it is, this is something that is not in normal programs, these type of things, as far as I know at least. Okay, what about completeness? I will show you a sufficient condition for completeness, and I will show you examples where this condition doesn't hold and completeness is not, we don't have completeness in these cases. So the sufficient condition requires the following definition. We call two functions reach equivalent. I will show you this by example. When do we say that A and B are reach equivalent? They're reach equivalent if, look at these recursive calls. So if the conditions under which these calls are being made and the arguments that we are sending to these functions are the same, if it's true about every function that we're calling on both, then we say that the two functions are reach equivalent. This is a very strong condition, but it is sufficient to it is sufficient for completeness, or sufficient under some assumptions.
Is this a syntactic condition, or is it a semantic condition?
It's a semantic condition. No, of course you can. Of course, the condition here can be made out of 3 consecutive ifs, and here 1, for example. Okay, so this is just a formal definition of what I said before, so don't bother to read it. But the idea is that the rule that I showed is complete for rich equivalent functions. Okay? It said under some reasonable assumptions, we can show some examples in C where even when this condition holds, it is still not complete, but these are mostly unnatural examples, I would say, like things that have to do with dead code and stuff like that. So this is good enough. So let me show you examples where the rule is not strong enough. It's not complete. Okay? So think about these two functions, f and g, that I want to prove equivalent. What these functions do, they just compute the sum from 1 to n. Okay? The difference is that this does it in twice as fast as this one. Okay, this is going to be n steps, and this is going to be n divided by 2 steps. Okay? And I'm not going to be able to prove partial equivalence in this case, although they are partially equivalent. And the reason is that, remember the premise, what I should do is replace these with uninterpreted functions, right? So what happens, so look at here, the problem is that they are called with different arguments. And since they're called with different arguments, and these are uninterpreted functions, it means that I cannot assume anything about their return value. And as a result, this is going to return n plus some non-deterministic value, and this is going to return n plus n minus 1 plus non-deterministic value. And I can tell you that in most kind of like classical loop transformations that compilers do, for example, in most of these cases, the rule is going to fail, actually. Like if you do like loop reversal, it's going to fail. If you're going to do loop splitting, it's probably going to fail. The question is how many of these loop transformations are being made in practice? That's a good question that I don't know to answer. Okay, you guys can answer this question probably better than I do.
So given two
Yes.
programs, can you check whether they're reach equivalent?
Yes. Yes, I can check that. This is one example. Here's another example. Here they are actually called with the same argument, but it's still going to fail. By the way, in the previous example, they're obviously not reach equivalent, right? Because they're called with different arguments. Okay. Here it's again, they're called with the same argument, but not under the same conditions, because this one is going to be called when n is equal to 1. This function is going to be called, where n is equal to 1 here, this one is not going to be called. And look what happens when n is equal to 1. Okay? When n is equal to 1, this one returns 1, and this one returns 1 plus some non-deterministic value. Okay, so therefore I'm not going to be able to prove this equivalent. Okay? Now I have this button here, which is a link to another presentation, which anybody who is interested enough and has the time is welcome to stay. So this shows some results that we have from the last months and a half I worked with in the Software Engineering Institute with Sagar Chaki and Ari Garfinkel. So we actually solved these problems for these two particular problems. With very simple function summaries, these problems are being solved. Why? I'll just give you a hint. For example, when n is equal to 1, I can actually compute what these functions return, right? I know that when n is equal to 1, it returns 1. So I can just like compute explicitly this information and add it to the uninterpreted function. So it will know that when I call it with the argument 1, it returns 1 and not a non-deterministic value. So this type of analysis is possible for some cases. It solves these specifically these two cases in many other cases. But again, I'm not going to show this now, only for people who are interested. So I don't know how I'm doing it with respect to time. So far I talked only about partial equivalence. I have 3 slides talking about how to prove mutual termination. It's another proof rule. And then I will speak about the system for the prototypes. I think I do have time, right? So mutual termination, the rule, this is the rule, mutual termination. What it says is basically 2 things that we already know. So if the 2 functions are both partially equivalent, suppose we already proved it with the first rule, and in addition I can prove that they are reach equivalent, then these 2 functions mutually terminate. This is a strong requirement, this thing. And actually it can be weakened. This is the type of things that we're currently thinking of, is how to weaken this rule. Okay, but at least in this version, at least it's it's reasonable to try to prove that it is sound. It is sound. We prove that it is sound. Okay, so how do we prove rich equivalence? I'm going to show you now. So suppose that we want to check the same two programs. We want to check whether they mutually terminate. So remember, this is already after we replaced it with the uninterpreted functions. So how do we know if they're rich equivalent? Well, we have the guards, right? We have the guards. We know that when b is different than 0, then we call this one. And when y is greater than 0, then we call this one. And we have the arguments. We have the arguments with which these two functions are being called. So we're just going to collect this information. Okay, so we have, again, the guards. This is what I painted in red here. And the arguments. So we can just write the condition saying that, okay, if we have equal inputs and the transitions, this implies that we have equal guards. And when the guard is true, then they are called with the same arguments. Okay? If we're able to prove this, then we proved rich equivalence. Okay? In this case, this verification condition is indeed valid, and indeed these two functions mutually terminate. Okay, so I'm done with the rules. I'm going to talk a little bit now about this prototype that we built. It's called the Regression Verification Tool, or RVT. So given two C programs, the first thing we do, we eliminate all loops. We turn them into Taylor recursions. We have this heuristic for mapping functions and global variables and types and so forth between the two programs. We can also give the user, the user can also specify manually a mapping or additions to the mapping. After we do this, we decompose to the granularity of pairs of functions according to the algorithm that I showed you before that goes bottom up. And one thing that is left that I still need to show you is how do I actually generate the verification condition given two functions. So remember that now we're trying to prove the equivalence of two functions that have no loops and no recursive calls. Okay, they might have some other functions that they call, but there's no recursion. And this can be done with a tool called CBMC. And I'm going to dedicate a slide to CBMC. CBMC is a tool that, it's a bounded model checker that was developed by Daniel Koenig. Anybody who knows, okay, actually before that, anybody who knows CBMC knows that the normal use of CBMC is that you give it a bound on the number of iterations and the depth of the recursion. And then it just breaks your program into a big verification condition. It can be either like SMT type of verification condition or a propositional logic formula. And then if it finds a trace, then this is a real counterexample. But we are using this CBMC in a very degenerate way because we don't have loops and we don't have recursive calls. So we basically just give it a flat program. But it's still good because it still deals with all the mess of C. And this is exactly what we need. CBMC has a construct called assume, which lets you add a constraint on anything you want, basically. But what we do, we use assume to enforce equal inputs. And we use an assert to demand equal outputs. Uninterpreted functions are not supported directly by CBMC, so we are building a C function that emulates an uninterpreted function. It just records the values that it received so far and the non-deterministic values that it returned in the previous time it was called with these input arguments. So now comes the mess. Yes?
Can't you model the uninterpreted functions as arrays, multidimensional arrays?
It is actually modeled as arrays, yes. So what we do is, so what happens is that we have the two sides, right? The program on side 0 and on side 1. So on side 0, whenever you call the function, you store the, okay, so there is some kind of an array which records the input-output relations from previous calls, okay? And then every time you call this function, you just ask whether you called it before already, and if yes, then you just return the values you returned last time, and if not, you just give a new non-deterministic value. Okay, that's exactly what we do. Now, there are some complications that makes our life much harder, and that is that remember that so far when we talked about proving partial equivalence, we said something like, okay, if the inputs are equal, then the outputs are equal. But what happens if these inputs are pointers? Okay, then it's meaningless to ask whether the inputs are equal, because obviously you do not expect it to be the same address, right? So what we need to do in these cases, what we do in this case, so we can look at the type of the pointer. If this is a dynamic structure, we can unroll it several times, basically build a non-deterministic dynamic structure of a specific depth. I will speak in a second what is this depth. And send, so it's like, suppose it's like a linked list or something. Okay, so we send both sides non-deterministic linked lists. They're going to have the same length, and their payload is going to be non-deterministic but equal on both sides. Okay? Now, what is the depth? Well, we can compute this depth, in theory at least. We can go over the code of the function. Remember that the code of the function doesn't have loops. So we can try to follow, are you doing like, you refer to the payload and then you do like p equal to p next. So we actually need 2 or 3 and so forth. You can try to guess this. It's not always going to work, because you can do, in C you can do, you do the address plus x, for example, and then, reach something. So these things are very hard to get. This is like the type of stuff that everybody who deals with C programs, analyzing C programs, knows all these complications. So again, we can either do our best in guessing the length, the size of the structure, or we can let the user declare it. But then we can add an assertion inside, asking whether we in the program, this x that we talked about as p plus x is larger than what we guessed. So at least it will fail if we guessed too low. So these are the type of things that we're still, it's still under development. But and the arrays, of course, have the same problem. We can try to guess the size of the structure and add appropriate assertions. Okay, I will just talk to you about one more feature that this system has. So far we talked about partial equivalence. It was like I/O equivalence, but the user may have a need to specify his or her own equivalence specification. So for example, the user may say that at specific locations of the program, if certain conditions hold, he expects the values of these expressions to be the same. Okay? So what we let the user do is we let the user declare these pairs of triples, like label condition expression. And what we do, forget about all the text here, don't even read it. What matters is this. So we just record an array of values. What is this array of values? It says each time I hit this location, label 1 in program 1, and this condition was true, I recorded the value of this expression in this array. And then in the end of the program, we check them pairwise that they are equivalent. Okay, so this way the user can specify something more specific, a more specific equivalent specification.
This is instead?
No, it's in addition. It's in addition to the I/O equivalence. Okay, so the system, the way our system works is, so we have the two versions of the program. This kind of summarizes the architecture. We have the two versions of the program. This is our tool. Basically what it does this decomposition algorithm. I told you every time it generates a small C program that it sends to CBMC. What does this small C program include? It includes a call to the two functions that we want to prove equivalent sequentially, one after the other. But before that, we generate equal inputs, equal non-deterministic inputs, and in the end, we add assertions that the outputs are the same. So this is all the things that we do here. We have to rename globals, enforce equality of inputs, assert equality of outputs, add these checkpoints. Checkpoints is what I talked about in the previous slide. It doesn't matter, let's not go into all of these things. And then we get, in the end, we can get a counterexample. The counterexample, of course, may be spurious because of the non-completeness of the rule. Again, another research topic can be like how to deal with this and how to try to refine it and so forth. All of these things are in the future work list. Here is a picture of our system. This is an Eclipse plugin. What I want to show you is that the output of our system is not just a yes/no answer. It gives you, in addition to the graph. So these are the two call graphs. It kind of colors the different. First of all, it tells you. Oh, this is actually an old version. Sorry. So this doesn't show you the mapping, but in the new version, it shows you like which function was mapped to which function, and the color says whether the system was able to prove them equivalent or not. And some function, for example, these are library functions. Then library function, we have like a file listing library functions that we have to assume that they are equivalent. So this is why it doesn't color it in this case. So the output is more complicated than yes, no. It gives you a list of all the functions, all the pairs of functions that it was able to prove equivalent, in addition to the graph. Some experiments that we did, I'm not going to go in detail in all of these things, but let me just say that the whole system is very academic alpha-ish. It's definitely not industrial strength. We were able to prove the equivalence of some industrial programs, some MATLAB examples. It is still, what we really want to do is to take like real archives, like real like CVS archives, and actually prove equivalence reflecting real changes in the program. So we didn't reach that point yet, but at some point we will reach that point. So what we did with these programs, we just manually inserted all sorts of code motion changes and all sorts of things like that, and we were able to prove it. Usually, our observation was that when the programs are equivalent, we normally did not have problem proving it. Like, I don't think that even once we had a problem because of the incompleteness of the rules. Like, the only times we had problem with the incompleteness of the rules and where we tried to find examples where this rule is going to fail. And it usually solved it in minutes. When they're not equivalent, then, of course, the proof fails. But then we have also kind of like a backup mechanism. Then we try to prove K equivalence. We just unroll the programs and perhaps we can try to find a bug, find traces that prove that they're not equivalent. So to summarize, regression verification, we think it's an important problem. And it's important because if we will be able to solve this problem one day, it has a better chance to succeed in the industry than functional verification. This is what we think. It's a very kind of a strong statement. It's not established in any sense. It's just kind of a hunch. It's a grand challenge by its own right, the same way that functional verification is a grand challenge, but we still think it's much easier than because of the reasons that I mentioned. I have another slide about future research, but let's end here. Okay? Thank you. Yeah. Here's the thank you slide, yes.
It seems like sometimes you don't want quite equivalence. You want the equivalent for a lot of different things, but then perhaps you've added a new feature.
Absolutely.
So then it'd be nice to be able to say, to run your tool or run an equivalence on something except whatever it is.
Yeah.
Do you have some way of
Yes, of course. Yes, of course. So first of all, remember that the output is not just, as I said, it tells you what is equivalent and what is not. This is one thing. With this equivalence specification that I mentioned, you can add conditions there, if you remember. So you can say that only when this flag is turned off, for example, then prove that they are equivalent. Things of that sort. And the user can always add assumptions. You can use an assumption, assume that this flag is turned off, and so forth. But one thing that I didn't show you in the future work thing is that it's an interesting problem how to characterize concisely the cases for which the programs are not partially equivalent. That's an interesting problem, right? You will get a counterexample. Okay, but the counterexample doesn't tell me much because it's too detailed. Can I somehow use perhaps like some type of predicate abstraction analysis in order to get predicates that describe in which cases the two programs are different? Things of that sort. Yeah, it's definitely an interesting problem to work on. Okay, yes?
So the uninterpreted function you assume is set back to 3?
Yes. So an uninterpreted function, it has has inputs and has an output. Like, yeah, so, okay, so what we do is the function that you're abstracting with an uninterpreted function has a list of inputs and a list of outputs. So the only thing it does is it gives you non-deterministic values for the outputs, but it maintains consistency. That is, if you're calling the function twice with the same arguments, it gives you... so side effects are part of the outputs. That's the short answer. Okay? Okay? Yes?
If I understand correctly, the thing that you send eventually to CBMC is some kind of sequential composition of the two functions.
Mm-hmm. That's right. And these are usually typically easy to prove because it's small programs, no loops and so forth. Okay.
So when you get a counterexample,
Mm-hmm.
what you said is that you can prove that two programs are reach equivalent, right?
Mm-hmm.
To check for the feasibility of the counterexample, you could just run this reach equivalence, and if that returns true, then it's a true counterexample, right?
Because of what I said that the rule is complete if they are reach equivalent.
Right.
Yes. Yes, I guess so. But remember, they had this little starter saying that there are some cases that even when they're reach equivalent, then the rule is not complete. But yes, in theory, we can do something like that. Absolutely. Okay.
Stand the speaker.
Yes. Thank you.